So we've just introduced this concept of distributed loads. I've got a simple example. Let's work here. Let's say that I've got, in the next chapter, we're going to talk about pins and rollers. We can introduce them kind of right now. Let's say I put some sort of a pin structure on this end and a roller on that one. And again, we're very soon going to talk about what that means. And we're just going to apply a very simple distributed constant rectangular distributed load here. These will always come out in units of force per distance. So let's say I've got 2 pounds per foot. And let's say I've got a distance here of, I don't know, we'll make it 4 foot. So a 4 foot distance there. Okay. And what we want to do is we want to replace with a single force. So we'll replace this distributed load with a single force. Now, if we go hardcore on this and we do the calculus, just to show you it's pretty simple, especially with some of these. We mentioned last time, hey, if you've got a rectangular load, just find the area of the rectangle and you put it there. But if we show you, again, we did mention you have this formula, right? And this is your resultant force, is the integral of W with respect to X along the entire length, and you find the location of it where I integrate X times that WX with respect to X. So let's just do the calculus real quick here. So that resultant force then is going to be the integral across the length of whatever the distributed load is as a function of X with respect to X, or Y, or whatever direction we're going. In this case, we're going in the X direction. So what do we do here? Well, I'm going to plug in, this is my W sub L, right? So I'm going to integrate across the length. Well, the length goes from 0 to 4 foot. I've got 2 pounds per foot. I'm going to integrate that with respect to X. Now, the 2 is a constant, so it comes out of the integral. Units are always considered a constant whenever you're dealing with them mathematically in calculus. All rules, whatever rules you apply to a constant in any form of math, apply those same rules to units because they represent some constant known quantity. So I'm going to pull all that out, 2 pounds per foot, that all comes out of the integral. And now I'm just integrating from 0 to 4 foot with respect to X. Well, integral of dx just becomes X. It's the easiest integral. Integrating a constant is the easiest integral to integrate. So 2 pounds per foot times X from 0 to 4 foot. I'm going to plug these in. So FR 2 pounds per foot. I'm going into painful detail here. You don't necessarily have to do this every time, but the first time we do it, it's good to go into painful detail. So I plugged in for X here, 4 foot, and then 0. So the resultant force then is 2 pounds per foot times 4 foot, so that just leaves me 8 pounds, and then 2 pounds per foot times 0, so 8 pounds minus 0, or 8 pounds. That's the resultant force, which makes sense. I've got a rectangle here, 2 pounds per foot tall, 4 foot wide, multiply the two together, that gives me the area, it gives me an 8 pound force. That's easy. Just wanted to show you. The calculus does work. So when if you do have to do it on something more difficult than rectangular load, you have at least a template of how to do that. How do we find where this guy gets located? Well, again, X bar, the location of that force. Now we've just done this. We found the resultant force. Now I need to integrate X times that WX along the length. So the integral from 0 to 4 foot of X times whatever WX is, well, our WX we've already found is 2 pounds per foot. So I'm going to plug that, rather than writing W as a function of X there, I'm going to write in my value for W as a function of X. That's 2 pounds per foot. It's a constant. I'm going to integrate that with respect to X. And that's going to get divided by then, again, the resultant force. Right? This guy that I've already found, this integral W sub X, or W of X, with respect to X. So we've already found that guy. So we can just carry around either 8 pounds or FR, whichever you like to carry around. Here we're going to integrate this top, so let's do that. Pull the constants out. Again, units are constants, numbers are constants, so 2 pound per foot, that's all constant that comes out. I'm now integrating from 0 to 4 foot, x with respect to x, and that gets divided by, again, either the 8 pounds or the resultant force. Okay, now I'm integrating x with respect to x, so I've got, leave this 2 pound per foot up here. I'm going to go ahead and divide by the 8 pounds, that's this FR. All right, so go ahead and divide by the FR. I'm going to pull all that out, and here I'm going to integrate x. So the integral of x is just x squared over 2, and that's going to go from 0 to 4 foot. So you can simplify this if you like. This is 1/4. That's 2 over 8 is 1/4. I've got pounds on top and bottom, so I'm left with per foot, or the units that are left. Okay, and then what do I do here? Here I've got x squared divided by 2, so I'm going to have 4 squared is 16 divided by 2 is 8, and the units there are going to be feet squared, because the 4 foot gets squared, so that's 16 feet squared divided by 2 is 8 square feet. And then minus that 0, so it's 0 times 0 in for x squared, that's 0 squared divided by 2, that's still 0. Okay, so I've got 1/4 per foot times 8 foot squared. X then becomes, I've got 8 divided by 4, that is 2. And I've got foot squared divided by feet, that is feet. So the x bar value then becomes 2 feet, which again probably makes sense. If you look at this guy, we should be able, we said earlier that common shapes, this is the previous page, if I've got a rectangular load, I can apply this constant times the length, that's my resultant force, and apply it at half the length, which is what we find here. I've got the 8 pounds applied at half the length, which is 2 feet. So this is kind of a smaller problem when we get further along in the class. What you would find is this would just be part of the problem. Would be that they would give you this distributed load and they would ask you some other things about this thing, but in order to find the other things, probably like what's going on here and what's going on there, that's what we'll start doing in chapter 5. To do that, you're going to have to be able to convert this into this. And if it's a triangular load, you'd go through the same similar procedure. You wouldn't have to do, by the way, we've done the calculus now one time. You don't have to do the calculus. Same thing here. You don't necessarily have to do the calculus on a triangular load. We could. I'm not going to spend a lot of class time to do that. It's pretty simple though, right? This is where K is, this B is something like 3x pound per foot or something like that. And then there just would be integrating that function. But the math is already done. You're welcome to use this. Now if you've got something like a third order polynomial or a square polynomial, then yeah, we'd go through and we'd do the calculus. So this always works, but these are the two most common shapes that you'll encounter: a rectangular and a triangular load, and this is how you would do it. And find the area, put the force in the middle. With a triangle, you have to find the center of the triangle, and that's going to be 2/3 length from one end, 1/3 from the other. And the area of the triangle is 1/2 base times length, essentially. Right. So here we've done just a rectangular load. Okay. What's next then? What are we doing next? All right, so that basically is the end of chapter 4. There's a little bit of discussion about cables and ropes and chains, things that actually have weight to them. That's beyond what I normally like to talk about in a statics class. There's plenty of other stuff that we need to get to, and we just simply don't have time to really spend a lot of time on those. But those appear as distributed loads. But all that to say, you will encounter distributed loads throughout the rest of this course, so we need to make sure that we understand what we're doing there. And it's really just an equivalent force systems application. That really kind of rolls us into, for us, it's going to be in the Hibbeler text. That's chapter 5 is where we pick up after that. And chapter 5 is where we basically apply equilibrium to what we call rigid bodies. Now, what we mean by rigid bodies, rigid meaning bodies that do not deform, right? Bodies that do not lose their shape. Many of you go on to take a strength of materials or mechanics of materials course, and that's where you'll start to look at things that might actually deform in this shape. But the difference, where in chapter 3 we looked at equilibrium of particles. Again, remember, a particle is something that has some mass or some shape, and you can model it as a single point and get the same result. However, note here that because things like this, where I've got to locate this as a specific place, it's not just a particle where, oh, we'll just apply this force anywhere. No, to preserve what's going on here, I actually had to locate that force in a specific place. So we're going to apply that principle, that idea behind equivalent force systems, throughout the rest of the semester, and that's basically rigid bodies are things that we can't model as particles. The shape matters, right? So what we find is that most structures we encounter are supported by, let's say, or instead of support by, let's say supported or restrained so they remain in equilibrium. Those supports must impart a reaction force and or moment to counteract any system of forces applied. I feel like I should make some PowerPoint slides for some of this stuff. The basic idea is and so what you'll find is there are different fasteners you will encounter which impart different reactions. And so we're getting pretty close to a good stopping place. I'm going to show you some examples of some reactions in the next video that we'll look at, and we'll talk about what kinds of forces and or moments that they apply. So we'll stop there. We'll pick up the next one.